Right, so this week we'll focus on two sections, 6.3 and 6.4. 6.3 focuses on graphing sine and cosine, and then all the transformations. 6.4 focuses on the other trig functions. So your tangent, cotangent, secant, cosecant. Okay, so first of all, these kind of functions, they look a little different than functions we've drawn before. Okay? They have kind of a repeating pattern to them. Okay, the y values keep repeating themselves. And just to show you kind of what that looks like, I'm going to show you the graph of sine. Okay, so if you look at it, what's happening there is it's a wave. And the y values just keep repeating. So if you start at the origin, we start at 0. We go up to 1, down to 0, -1, back to 0, and then it's going to do it again. 1, 0, -1, 0, and keep repeating that pattern. So the y values keep repeating over a given set of x values. Okay, so what do I mean by a given set of x values? Okay, what I mean is there's a certain amount of distance you have to go through, left to right, before the graph repeats. Okay, if you wanted to mark it on the screen, here's the distance you have to go through, what's between those two red lines, and then the graph repeats itself. So you could take what's inside the two red lines, make a copy of it, and then paste it left and right forever, and that would be the picture you see. Okay, so between those red lines, that's called a section of the graph, or actually a more specific name is called the period. It's the amount of time it takes for the y values to start at 0, hit the highest, hit the lowest, and then get back to the starting point. So if we don't change the graph at all, if you just leave the graph as the original, you don't shift it, you don't stretch it, you don't do anything to it, you have to go from 0 to 2 pi before the graph repeats itself. So the basic sine and the cosine function repeat themselves every 2 pi radians. Okay, so just to be a little clearer about what we're graphing. On the x-axis, you're plotting an angle. Okay? And I labeled it in radians up above. Okay, so on the x-axis, that's an angle. On the y-axis, that's the sine of the angle. In this particular case, could be the cosine, could be the tangent. Okay, so the y-axis is trig function of angle. Okay, let me show you the graph of cosine, just to put it on the same screen at the same time. So cosine and sine look very similar. In fact, can anyone describe what you could do to the blue one to turn it into the red one? What kind of transformation? Leo?
Horizontal shift.
Yeah, it's a horizontal shift. If you shift the blue graph to the left, and it's actually a horizontal shift by 90 degrees, okay, or pi over 2 radians. That's the difference between sine and cosine. Their phase shifts of each other by 90 degrees, or pi over 2 radians. Most of what we do this week is going to be in radians. Okay, so that's why I'll mention some things in degrees to make some points a little clearer. But when we graph things by hand, we're always going to label our x-axis as an angle in radians. All right, another name for a period of a graph is also called one cycle of the graph. And we don't use the term cycle as much, but there are other fields, other trades that do use that term. Does anybody study electricity at all? Anything with electricity? Yeah. So with electricity, there's a couple things that are important. One thing is voltage. So in this room, we have 120 volts. But there's another thing that's important about electricity too. And it's different in this country than it is in most European countries. Anybody know the other thing? Yeah?
Frequency.
The frequency, exactly. The frequency, which is measured in hertz, which means cycles per second. So when you talk about the frequency of alternating current, in the US, it's 60 hertz. And hertz means cycles per second. So if you had a device you could plug into the outlet and see a picture of the electricity, kind of like an oscilloscope for electricity. An oscilloscope shows you a picture of sound. Well, they have the same kind of thing for electricity. You would see an electrical wave going like this, 60 times per second. Okay? A little different when they measure electricity because it's not measured as an angle. The x-axis is a time unit. So from 0 to 60, it would go up and down. It would go up and down 60 times. 60 times per second. Per second. Any questions on that notation? Using hertz. Also, another thing is, even when you get down to 1, it's still 1 hertz. It's not 1 hertz. Because hertz, it's named after somebody. That was the person's last name. So it's not plural. It's just named after someone. Right. So let's take a look at these two graphs. I'm going to graph sine negative x and then negative sine x. And just look at the difference between the two. What happens to the graph when you put a negative either inside or outside? What does a negative cause a function to do? Yep. Yes, exactly. It causes it to reflect over the some kind of reflection, either the x or the y-axis in this case. Well, whenever you put stuff inside the function, that's your horizontal. So the one on the left that I just typed in on the calculator, that's a horizontal reflection. The one on the right, okay, that I'm typing into y2, that's a vertical reflection, okay, because when you put a negative on the outside of the function, that causes vertical stuff to happen. So let's see what the difference is between reflecting the graph horizontally and then reflecting it vertically. What's the difference between reflecting it horizontally or vertically?
There isn't one.
There isn't one. You can't tell the difference. And what that means is the graph of sine is symmetric about the origin. All right. Let's try something a little different with cosine. I'm going to try graphing cosine, and I'm going to do a reflection, a horizontal reflection. So horizontal means over the y-axis, right? It's left to right. And then I'm going to graph the original. Let's see what happens here. So we've got cosine negative x and cosine x. And kind of a similar thing again. Can't tell the difference. So that means, in this case, cosine is symmetric over the y-axis. If you reflect cosine over the y-axis, you can't tell the difference between that and the original. Any questions on that? Yeah.
When I put those into graph, it only makes straight lines.
And you do adjust your window?
Yeah, I do.
You did? And how did you adjust it? What did you do?
I did zoom 6.
You did zoom 6? All right, so when we graph a trig function, you want to do zoom 7.
Oh, okay.
Because what's happening, if you do zoom 6, that's going to set a window from -10 to 10. And depending on your mode, like if I was in degrees, to see a full cycle of sine, I have to go from 0 to 360. So if your window is -10 to 10, that's nowhere near 0 to 360. Okay. So zoom 7 will do different things depending on your mode. If you're in radians, it's going to set a window like that. It's about -8.6 to +8.6. If you are in degrees, and you do zoom 7, you're going to get the exact same picture because it just changed the window. Okay? It's not -8.6 to 8.6. Now, it's -495 to 495. So we'll practice later on. Like, let's say I wanted you to graph this and show me exactly one cycle on the screen. Well, if we know that the width of one cycle is 360 degrees, that's exactly one cycle of cosine. You're just seeing one dip, one section. Another way I could show you one section would be -180 to 180. The point is that cosine has a period of 360 degrees. So any window that has a width of 360 degrees will show you one cycle of the graph. In that case, you're looking more at the upward part of the cycle instead of the downward part. Okay, any questions on that? It's a good question about setting the window. All right. So generally when we graph sine and cosine, because they're a little more complicated, you need about 5 points. And these are the 5 points that I recommend picking. 0, pi over 2, pi, 3 pi over 2, and 2 pi. And if they seem kind of random, they're really not. Okay? If you change all those numbers to degrees, you can see what they are. 0, 90, 180, 270, 360. So those x values that I picked are just 5 equally spaced points from 0 to 360. But we are going to write them in radians. So for that part of the cycle, by picking those 5 points, you're getting the start, the stop, the highest, the lowest, and what's right in the middle. That's perfect. So it'll give you one cycle. Okay, if you were to extend this graph a little bit, say you extend it that way, let's see. What I just put a box around, that's also one cycle. Lowest goes to the highest, back to the lowest. Okay? So you could take that box and drag it anywhere you want, and what's inside it, you're always looking at one cycle. In this case, highest, lowest, back to highest. Generally, when you're asked to sketch one cycle or one period of the graph, we sketch the first positive cycle. Okay? There's nothing wrong with sketching a negative part of a cycle, but generally I'm going to sketch the first positive one. All right, so what I want to do now is come up with a table that gives us the coordinates for sine and cosine for the first positive period. Now, this is going to be a table that's, we're going to call it the original table. It's going to be a table that we haven't done any shift to it, We haven't done any stretching. We haven't done any reflecting. Just the basic function before you do anything to it. Alright, so let's, in that picture that I have up above, that's a pretty accurate sketch of sine. Okay, don't worry about cosine right now. I'll come back and we'll look at that one in a second. Let's just focus on sine. Okay, so looking at the graph up above, when x is 0 in that graph, Shauna, what does it look like the y value is when x is 0?
0.
Yeah, 0, 0. So the sine function starts at the origin. Dylan, how about when my graph hits pi over 2?
1.
Yep, we're up at 1. Gracie, when I hit pi,
0.
yep, I'm back to 0. And then 3 pi over 2. Sam?
Pi. Oh, sorry, which one?
Yeah, go ahead. But yeah, go ahead.
Which, can you?
Oh, 3 pi over 2?
Oh, back to 1. Or, sorry, negative 1.
Negative 1. So 3 pi over 2, we hit our lowest value. And then, Sam, h, what about at 2 pi?
You're back to 0.
We're back to 0. Okay. So that is the starting points for sine. It's important because any transformation we want to do is based off those 5 points. So if we have those wrong, then the transformation comes out wrong. Okay, let's look at a graph of cosine. And I'm going to do it in radians. And what did I say the period for cosine was? What's the period for cosine? Oh, Caleb? Yeah.
2 pi.
2 pi. So what I'm going to do is, in order to show one period on the screen, I'm going to set it from 0 to 2 pi. The scale, it isn't really important, but if you want to place nice tick marks equally, set the tick marks to pi over 2, and you'll get one at every quarter point in the period. Highest and lowest, you've probably seen a pattern. These graphs aren't going above 1 and below negative 1. So negative 4 to 4 is fine. But there's one cycle of cosine. Okay. So now when we're at 0, we're at the high point. We're starting at 1. When we get to pi over 2, we're at 0, negative 1, 0, back to 1. And those are the 5 coordinates for the first positive period of cosine. Okay. Any question on those 2 tables? All right. So pretty much everything that I've given you up to now is just kind of background information. I haven't talked about any transformations yet. Okay, now I'm going to talk about transformations. Okay. For now, up until we do multiple transformations in the same problem, when you look at those original tables, one column is going to stay the same, the other column is going to change. Because for now, I'm only going to give you one transformation per problem. So say, for example, in the problem it says to do a vertical shift up 5. That's going to be it. Just a vertical shift up 5. So if you think vertical, vertical is the y-axis. So if you do something vertical, the y's are going to change, the x's stay the same. Once we get into multiple transformations, like let's say I give you a problem that says shift the graph up 2 units and then stretch it by a factor of 2 horizontally. Well, now we're changing both the x's and the y's if you shift something up or down and stretch it horizontally. Okay, but we're not going to get to multi-transformations until 6.3, part 3. So the first transformation I'm going to talk about is called a phase shift. Now, it's a transformation, you've done it before, but we've never called it that. When they talk about periodic functions, they generally call a horizontal shift a phase shift. But it means exactly the same thing. So phase shift, let's see. That's when the graph moves left or right. So just as an example, what would happen if you graphed the square root of x plus 2, where the x plus 2 is all under the root? Which way would that graph be shifted? Yeah.
To the left, too.
That would be shifted to the left 2 units. Yeah. If you had the log of x plus 2, that would be shifted left 2 units for a log function. If you had a parabola, x plus 2 squared, that would shift the parabola left 2 units. Well, it's exactly the same for sine and cosine. If you add or subtract inside parentheses, that's a horizontal shift. And it's the opposite of what you would expect. Okay? Everything that's horizontal is always the opposite. Plus is going to shift left, minus is going to shift right. Okay, so that part you should already know from all the transformations we've studied all year. But minus will shift right, plus left. And a lot of times what I'm going to do when we study a transformation is I'm going to relate it to some concept. What I'm going to stick with for most of the week is sound. So when we study a phase shift or a period change, we'll look at it mathematically, but then we'll hear what it sounds like. Sound isn't the only application for sine and cosine waves. There's lots of other applications. But sound is kind of neat because you can kind of hear what's going on. At least for most of the transformations. There's 4 transformations. There's your vertical shifts and horizontal shifts. Then there's your vertical stretches and your horizontal stretches. 3 out of 4 of those I can demonstrate with sound. One of them I don't know of any effect or any connection with sound at all. So for that one we won't be able to hear. But phase shift is one I can play a sound and you can hear it. Right, so let's look at how we do a phase shift. So what you have to do is take the points in the original table, either sine or cosine, whatever problem you're working with, and we have to adjust them. So if we do a phase shift, what are the options the graph could move in? Which ways could the graph move? Yeah. Left or right. And left or right affects which axis? Yeah, it affects the x-axis, which means if you do a phase shift and only a phase shift, the y's are going to stay the same. So you're going to go back to the table I just gave you in your notes, and you would copy down all the y values for sine or cosine. Okay? We'll do some problems where we do a sine, and we'll do some other ones where we do a cosine. Just copy the original y values, no change there. So if the y's are going to stay the same, then that means the x's are going to change. So, to find the new x values, the first thing you have to do is determine what has been added or subtracted inside the parentheses, okay, to the argument. So this problem, we are subtracting pi over 2. Now, which way is that going to move if you subtract pi over 2? It's going to move all my points to the,
Right.
it's going to move them to the right. So really, if I want x values to move to the right, what do you have to do to the x values? Do you increase them or decrease them? You increase them. So what you end up doing is you do the opposite. If you see minus pi over 2, you're going to add pi over 2. Okay, so you always do the opposite of what the problem says for a phase shift. Now you don't do the opposite for every transformation we're going to study all week, but for phase shift you do. So in that problem you would add pi over 2. How about that problem? What would you do to all your x's? You would subtract pi. You would subtract pi over 4. Okay, you always do the opposite for a phase shift. Not that hard to remember on its own, but then once you know all the transformations, you've got to keep straight. Wait, if this is a vertical shift, do I do the opposite or do I not do the opposite for vertical? Okay. Vertical is the next one we're going to study. And that one, it turns out, you just do exactly what you see. If you see plus, plus is up. If you see minus, minus is down. You don't end up with the opposite. But let's start out with a phase shift. All right, so first thing, y's stay the same. So I'm going to look at my table for sine, and I'm going to copy down the y values. Okay, can somebody remind me, what are my y values for sine? And when I say y values, I mean the first 5 y values for the first positive cycle. Yep.
0, 1, 0, negative 1, 0.
Okay, so there's our y values. Now, to get the new x's, first we're going to take all the original x's. Okay, so I'm going to start with those. Trevor, can you remind me, what are my original x values for sine or for cosine? They're actually the same.
0, pi
Yep.
over 2, pi, 3 pi over 2, and 2 pi.
Pi over 2 and 2 pi. And now we're going to take all of those x values, and what am I going to add to all of them? Yep. I'm going to add pi over 2. So what I'm showing here is the calculation. We have to actually do this. So what I would be grading is what I just put inside that box. Okay. So 0 plus pi over 2, that one's quick. Pi over 2 plus pi over 2, we already have a common denominator. So what do you get when you add pi over 2 to pi over 2?
2 pi over 2.
2 pi over 2, which I'm going to reduce to pi, but I want you to remember that it was 2 pi over 2, because I'm going to show you a pattern at the end, and you have to remember that. The next one, pi over 1 plus pi over 2. What do I have to do first before I can add those? Yep. Common denominator. And what would my common denominator be?
2.
2. So double the top, double the bottom. What's 2 pi over 2 plus 1 pi over 2? About, yeah.
3 pi over 2.
3 pi over 2. The next one, well, Tanya, I have 3 pi over 2 plus 1 pi over 2. How much does that give me?
4 pi over 2.
4 pi over 2, which, again, I'm going to reduce it to 2 pi. But now I want to go back and just look for a pattern. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. What's the last one going to be? 5 pi over 2. And if we were to keep going and start graphing the next period, 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2. You don't see the pattern as much once you reduce the common factors with the numerator and denominator, but you should reduce it. Okay, so there's your table. So on the test, the way I would grade a problem like this is you get 1 point for each y value, 1 point for each x. So that table would be worth 10 points. Any questions on the table? And now the sketch is worth 2 points. So now, y-axis, that's pretty straightforward. I'm going to label the highest as 1, and the lowest is -1. If you leave the labels off the axes, I'm going to assume you're always going by 1s, which would be fine for the y-axis. But do you think going by 1s on the x-axis is a good idea? Caleb? No, how come?
Because it's supposed to be in radian.
Yeah, it's in radians. I mean, you can label it 1 radian, 2 radians, 3 radians. But then the problem is you have to figure out what these decimals are. So now you're dealing with numbers like 1.57, 3.14, 4.71, 6.28. That's kind of messy to graph. So you can label an axis any way you want, as long as your labels are consistent. So we already know those labels are consistent. That's why we picked the starting ones we did. So if you look at it in degrees, that's 90, 180, 270, 360, 450. That's an equal gap between each one. So use those to label your axes. Pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2. Now you don't have to worry about figuring out any decimals. And now graph your points. So pi over 2, 0. Pi, we're at 1. 3 pi over 2, 0. 2 pi, -1. Back to 0. And remember, everything about this graph should be nice and curved. No sharp turns or anything on the graph. Okay, on the homework, you'll already have a grid, so you won't need any graph paper, and it's exactly the same thing on the test. The only difference on the homework is I give you spot to draw what the original would be, and then the new graph. Okay, that's the new graph. If you wanted to put the original, that would look something like this. In black is the original, in red is the new one. So you can see what happened. It's a phase shift. It shifted to the right. Any questions on that? All right, let's take a look at what that would sound like. All right, so now in terms of what that would sound like, okay, using this program, I can shift the phase. You really need 2 speakers to do this accurately, which I have inside the soundbar. And visually, okay, if you shift it and it moves, that's what it would look like. So there's a phase shift, it's just moving left to right. So what I'm going to do is I'm going to play that frequency. Okay, it's just going to be a single tone, so there's nothing else fluctuating about it, just the phase. Does anyone have a guess what it's going to sound like when I change the phase? How you're going to perceive that, how you're going to hear it. Well, what can you change about a tone? What's one characteristic that could change and you'd hear the difference? Oh, Gracie? Okay, the pitch could change, yeah. Could go from like a lower pitch to a higher pitch. Right? So that pitch could change. What else can change about a sound that you can hear besides the pitch? Oh, Leo? Any thought?
Tone. No.
how would tone be different than pitch? Okay. I didn't know if maybe you meant something else, and I was going to ask you to just explain what you meant. But some people talk about what they call timbre, which is the characteristic that makes a tone sound like a certain instrument, which I'm not changing that here. For example, if you play exactly a 1,000 hertz tone on a piano, and then you play that on a guitar, they're going to sound different, even though mathematically they might be exactly the same frequency, but there's some characteristic about the sound that you can hear the difference between a piano and a guitar. Just the way the frequency sounds, and they call that the timbre. But there's one other simple thing you can change about a tone. Have a guess what else you can change, or about any sound? Besides the pitch of it, you could change the volume. So you could change the volume. And really, besides the characteristic of the instrument making the sound, which I can't really do different instruments, I can just do a digital frequency sound. All I can change is, or the only changes you can hear are going to be changes in pitch or volume. So let's change the phase and see what that kind of sounds like. Okay, so what happened as I changed the phase? You want to explain what they heard? Yeah.
It was exactly the same.
It sounded exactly the same. Did it change for anybody?
Just a little.
It changed, Sam?
It got like quieter in the middle.
Yeah.
It's more
And it got quieter? Now for me, it got the quietest at this point, right here. Did it get the quietest for anybody right there? Some people say no. Some people say it sounded exactly the same. And that depends on where you're sitting. Because the characteristics of the room sound can echo. So what one person hears is totally different from what someone else hears. So when I play this, to me that's soft. It's getting louder. Now it's softer again. That's the way I heard it standing right here. But somebody standing in a different spot, maybe it was the loudest for you at this point. But for me, it was the softest. It actually got the loudest about like that for me. So phase shift is kind of an interesting effect. It's like you have two sounds, and the sounds can actually cancel each other out. That idea is used with like noise canceling headphones. You can cancel out certain sounds. This is a very easy sound to cancel out because it's very mathematical. It's a single tone, single frequency, constant volume. You can very easily cancel it out. And I do that when I record. There's a frequency that I cancel out. And if I can show you, it's the frequency of the bell. So if I can, let's see. So if you look at that, there's certain frequencies that I basically just have drop right off. There's lower pitch frequencies, okay, which are kind of caused by vibrations in the ceiling or the heating, cooling system. But then there's a couple frequencies that are not really towards the low end. They're definitely higher, and the fifth one is the bell. So what's happening is I'm recording. My voice is a lot of different frequencies. Okay, the way you hear it, that's what makes my voice sound like my voice and not your voice. But there's one particular frequency that I take out of my voice or out of this room when I record, and that's around 650 hertz. That frequency is gone from the recording. Can you really hear it, that it's gone? Not unless the bell rings. If the bell rings, you'll hear a very, very soft sound in the background. And it's not because the bell is soft. I mean, the bell is pretty loud. Everybody can hear it when it rings. But you won't hear it that well in a recording because I take that one frequency out. There's another frequency up here that, for some reason, I decided to take that one out too. But the fifth frequency, around 600 hertz, I just take that frequency and make it disappear from the recording. All right. So there's lots of different uses, for sound, and if you get into like engineering with sound and creating recordings and that kind of stuff, that's the kind of stuff they look at. You know, how do you get rid of the background noise, like a low hum in the background? And these are all things you probably couldn't hear on like a real cheap set of headphones. If you had a really nice stereo audio system, you would definitely hear this low hum in all my recordings if I didn't turn it off. There'd be like this vibration, very low hum, because the microphone is extremely sensitive. And those are frequencies that are generally below 100 hertz. Okay? So we'll talk more about what those kind of frequencies would sound like, and I'll play some for you probably tomorrow. Okay, any questions on phase shift? Yeah, let's try another one. Cosine of x plus pi. Okay, so first thing we want to make sure we identify is how do we know what transformation it is? Okay, so that is a phase shift. Can somebody tell me how we know that is a phase shift? By looking at the structure of the equation. Tessa, can you tell me how we know that's a phase shift? Because it what? Okay, it has one thing in it. So the fact that it has one thing in it besides the function and the x tells us there's only one transformation. But how do we know that that's a phase shift, besides the fact I haven't taught you the other ones yet?
You're adding pi.
Okay, you're adding, but the next transformation we look at is also going to be adding or subtracting. Where are you adding or subtracting here versus that? That makes it a little easier. Yeah.
You're adding in parentheses.
Inside the parentheses, so that x and the number are grouped together. Okay. Even if you, if you took this parenthesis and moved it here, you've completely changed the problem now. The x is no longer grouped with the pi over 4. Okay. That's how we know it's a phase shift. Okay, so phase shift. Dylan, what stays the same when we do a phase shift?
The y.
The y's. Can you tell me what my y's are going to be for, we skipped the cosine problem. I wasn't going to do 2 sine problems in a row, but we'll do the cosine problem as example 3. So can you tell me what my y's are for sine?
0, 1, 0, -1, 0.
0. And now I'm going to take all my x's, which are 0, pi over 2, pi, 3 pi over 2, 2 pi. And what am I going to do to all those x values? Yeah.
You're going to subtract pi by 4.
Yeah, subtract pi over 4. Now, I think after we do the first 2 or 3, you'll see the pattern. And you won't have to find the common denominator every time. But if you don't see the pattern, you can always do it that way. Just find the common denominator. So we have negative pi over 4. Now the next one, pi over 2 minus pi over 4. Common denominator there, yep, 4. So double the top, double the bottom. 2 pi over 4, take away 1 pi over 4. It's pi over 4. The next one, Trevor, what would be my common denominator there?
4.
4 again. So 4 and 4. And what's 4 pi over 4 take away 1 pi over 4? Megan? How much? Well, it still has a denominator of 4, right? It's kind of like just doing 4 over 4 take away 1 over 4. 3 pi over 4. Yeah, exactly. 3 pi over 4. Now, anyone think they know what the next one's going to be without finding the common denominator?
5 pi over 4.
Yeah, the numerator's going, the coefficient, if you can call it that, it's not really a coefficient because there's no variable, but the thing in front of pi is going up by odd numbers. -1, 1, 3, 5. And then the last one, 7. Okay, I think the shifts with pi over 4 are you get kind of the weirdest numbers or strangest ones to work with. And we also have to be careful setting up our graph. All right, but there's your table. Any questions on that? So the shift that we just did, pi over 4, what's pi over 4 in degrees? Understand? That's 45. Pi over 2 in degrees is a shift of 90. So the problem we're doing now is a little smaller shift than the one we just did. In fact, it's shift half as much. It's also going the other way. Plus is going to move it to the left. Okay, so let's set up our graph and see what's going on here. Y-axis, technically you don't have to label it because we're going to label it as 1 and -1. And that's, even if you didn't label it, I think that's what you should probably go by, 1 and -1. But x-axis, you definitely want to label it because we're not going by ones. All right. Just to avoid, because I'm going to have to write labels in here, I'm actually going to leave those off. You can keep them in your notes, that's fine if you can squeeze them in. But let's start with -pi over 4. I'm going to put that right there. The next label is positive pi over 4. Can someone tell me where that label would go? Where would the pi over 4 label go? Liam?
The first positive tick mark.
The first positive tick mark. Now, why can't you put it what I just put an arrow pointing to? Why couldn't you put it there?
That's 0.
That's 0. Don't ever put a label on the axis other than 0. So now, the next question, where does 3 pi over 4 go? All right, so we were just about to graph sine of x plus pi over 4. We had all the points in the table. Now it was just a matter of labeling where the points go. So the thing I was trying to get at here is, there's your gap between the points. That has to be the gap every time. You can't put 3 pi over 4 on the next tick mark because look what would happen if you did that. Now you just left a small gap between 2 points. Okay, that's not consistent. So if you end up skipping over 0, then you have to skip 1 every time. So 3 pi over 4, 5 pi over 4, and is that the last one I need? Yeah, 7 pi over 4. Now graph your points just like usual. 0, 1, 0, -1, back to 0. Sometimes it's a good idea to take all your labels and write them low, so that way you don't end up drawing over them. And that's it. So that's a graph of sine, and it's been shifted to the left just a little bit. Normally it would have started at the origin. Any questions on how you would do cosine? If not, I'll probably skip over the cosine one. The only thing that would be different is make sure you copy the y's from the right table. Okay, go to the cosine table. Okay, so that transformation I think is the harder of the two because you have to do arithmetic with fractions with pi. When we deal with vertical shifts, we're going to be affecting the y values, and the y values are super easy to work with. They're all 1s and 0s and -1s. Okay, so arithmetic is going to get a lot easier for these. Okay, so vertical shift, that translates the graph up or down. And what differentiates it from a phase shift is where you are adding or subtracting. You always add or subtract for a shift, but where controls, is it left and right, or is it up and down? So vertical shift is when you add a number outside of the parentheses. even if you put parentheses in like that, that's still a vertical shift. You would have to group the x and the number together to be a phase shift. And the reason I put D for the vertical shift, and I think I used, was it A for the phase shift? Yeah, I used A, is because once we learned all 4 transformations, you're going to have to do them in a certain order. Well, I'm kind of telling you the order as we go. So phase shift would always be first. Vertical shift is the last one out of the 4. And what's nice about vertical shift, you don't have to worry about the opposite. If you see a plus, is up. Bless you.
Thank you.
Minus is down. So if we're going to shift the graph up and down, what values are going to change this time? The x's or the y's? Yep, the y's. So what that means is the x's are going to stay the same. It's always great when the x's stay the same because you don't have to deal with any of those fractions with pi. So for every problem we do today and in the homework, for a vertical shift, the answer to your x's is going to be 0, pi over 2, pi, 3 pi over 2, 2 pi. Okay, so if the x's are going to stay the same, then the y's are going to change. To find the new y values, all you have to do is take whatever that number is and add or subtract it to the original y values. So again, arithmetic, it's going to be super easy. All you're going to do is add or subtract a number to a 1, 0, or a -1. Again, don't do the opposite. As far as a connection with sound, I told you there was one transformation. I really don't know the connection with sound, and that's this one. Stretching up and down, we'll learn what that does tomorrow. Stretching left and right, that has an effect. Phase shift, that's shifting left and right, has an effect. But shifting up and down, there's really no effect that I know of. Okay. Right, so first thing, I want to make sure we know what transformation that is and what about the structure of the equation tells you that. So Caleb, what kind of transformation is that?
That's a vertical shift up to.
And how do you know it's a vertical shift up to?
Because it's not x axis, like with cosine x.
Right.
Separated.
The argument is just x. There's no plus inside the argument or minus. Another way you can write that is like this. So you could see a vertical shift written 2 plus cosine x. That's the same problem. Okay, but if you want to move it to the end on the right, that's fine. Okay, so x values stay the same. Leo, can you remind me, what are my x values?
0, pi over 2, pi, 2 pi over 2, and, 3 pi over 2, and 2 pi.
Yep. And now the original values for cosine, we haven't done a cosine yet. So somebody else remind me y values for cosine, Gracie?
1, 0, -1, 0, and 1.
So notice I wrote them off to the side because we're changing them. And Shauna, what am I going to do to all those y values? Add 2. So we're going to get 3, 2, 1, 2, 3. And that's it. That's a vertical shift up 2. For the sketch, we're going to label our y-axis. If you didn't, that would be okay because I'm going by ones anyway. But x-axis, if you don't put the labels, it would be wrong. So we got 0, which you don't have to label 0. I know 0 is the axis, but you can if you want. Pi over 2, pi, 3 pi over 2, 2 pi. I got an extra line, I don't need it. Okay, so 0, 3, pi over 2, 2, 1, 2, and should always end where you started because that means you've drawn a complete cycle. Okay. Now that kind of looks like a V, but remember, it's this section of a wave, so it should have some curvature to it. And actually, in calculus, you'll learn what these 2 points are called. Those are called points of inflection. What that means is what's happening at that point is the curvature is changing. Between these 2 points, the graph is concave up. Okay? Concave up, you can think concave up, it would hold water. Like a dish, concave up. When you get into this section, and continuing on, which I didn't draw, the dotted line, that section is concave down. So the curvature switches right at that point from concave down to concave up. And if you drew that as a straight V, you wouldn't have any curvature at all. So don't do that. Okay, any question on that? Okay, so that's a shift up 2. And then we'll finish up with a shift down 3. Okay, so Juliet, since we're shifting down, we know the x values stay the same. So what are going to be my x values?
They're going to be 0, pi over 2, pi, 3 pi over 2, and 2 pi.
Yep. And now we're going to take all the original sine values. We did a couple graphs with sine, so hopefully you're starting to remember those. And Abby, what am I going to do to all those y values?
Subtract 3.
Yep. Can you tell me what you get when you do that?
Negative 3, negative 2, negative 3, negative 4, negative 3.
Negative
3.
Yep. Perfect. So there's our y, there's our chart. Okay, and now make your sketch, just like we did for last one. I would put the labels up above, then you're not going to draw over them. Technically, y-axis doesn't need to be labeled because I'm going to go by ones, but if you want to label it, perfectly fine. Okay, so negative 3, negative 2, negative 3. Negative 3, negative 2, negative 3, and then negative 4, negative 3. It'll be a little easier for you to line up the points because you're going to have a grid. But basically, I'm way off on that one. Basically, kind of like that. So there's your graph of sine shifted down 3. Okay, questions on that? Okay, so today we looked at all what we call the rigid motion transformations. All it does is take what you have and shift it to a new spot. It doesn't stretch or compress. Okay, tomorrow we'll look at what happens when we stretch or compress horizontally and vertically. Okay, so homework, it's going to be these 7 questions. Okay, I already have them on a worksheet, so you really don't need to copy them down. But if you lost the worksheet, you can always go online and you can get the problems there too.